right, good morning, ladies and gentlemen. I hope everyone is well today. Today we're going to begin exploring the concept of energy. So remember that physical science is an introduction to physics and an introduction to chemistry. So we're dealing with energy right now in the realm of physics. And in physics, the definition of energy is the ability to do work. Oh, we're blurry. Okay. The ability to do work. Sounds all well and good, but the question becomes, what is work? And so that's what we're going to define and do a little activity around today, so that we can understand this idea of energy before we explore it further. Before we do the activity to understand what's happening with work, um, let me tell you that energy is represented by the unit joules. There's a capital J. So when we were doing speed and acceleration, I could recognize speed because of the unit. If it's 5 meters per second, I would know that that's speed because of the unit. So likewise, if I have 5 joules, I'll know that it's energy because of the unit. All right. So before I literally define work, I want us to do the activity so we can explore the concept first. So today you should, at the end of our time together, you should be able to define energy, the ability to do work. You should know what the unit of energy is, and you should be able to define work. So we're going to do the activity, then I'm going to define it for you, and then we're going to do a few calculations to calculate for work today. So those are our objectives. I don't know why I'm looking there. So there. All right. So to do the activity, you need 4 books. So if you want to pause and go find, oh, stop being blurry. There we are. You want to pause and go find 4 books for yourself. Go ahead and do that. And I'm going to do it, and I'd like for you to do it with me, so that you can have literally the physical experience of work, so we can make the distinction between what work is and what work is not. Right? So if you were in class with me, I'd have you, well, pre-COVID, I'd have you do this with a partner, but in the time of COVID, you'll do this solo like you're doing at home. All right, so you're going to take 2 of the books and hold them in your hands, palms up. Okay? And all you're going to do is you're holding the books. All we're going to do is lift them up to our shoulders, bring them back down. And so this is experiential. And you want to think about the effort that you're having to put into this activity. Okay, so when I lift them to my shoulder and I bring them back down. We're going to lift them over our head. I'm going to turn them because it'll be easier for me to hold, which you can't see. So if I lift it over my head, if we compare and contrast, what was the effort to lift it to my shoulders versus to lift it over my head? Which one do you think required more? Which one felt like it required more? All right. So we're going to increase the amount of books. So we're going to put 2 books. I should have gotten some lighter books. We're going to put 2 books in each hand. I'm not sure I can do this with these books. 2 books in each hand. Okay, so now I'm holding 4 books, waist level. And I want to lift those to my shoulders. I really don't know if I can do that. Lift those to your shoulders. Let me get in the camera. There we go. Lift them to your shoulders, bring them back down. I want to advise you not to get heavy books. And then see if you can lift them overhead. I'm not going to try to do this with these 4 books that I chose because I see books raining all over my head if I do that. The objective was, okay, how much effort to lift to your shoulders, how much effort to lift over your head. The other thing you want to consider and test while you're doing the activity, I'm going to go back to just 2 books because that's what I can manage given the books I chose. Is there a difference between lifting them slowly versus lifting them quickly? Do you notice a difference? Lifting them quickly, lifting them slowly, okay? In doing that exercise, you actually just did work. When we think of work, we tend to think of the occupation. We tend to think of exerting energy, right? So if you have some chores at your house, if you have to sweep the kitchen floor, if you have to wash the dishes, it feels like work. Okay? But in physics, we have a specific definition for work. So work is done whenever you have to have a force and some movement. So work is the force being applied to an object over a distance. This over is not by dividing, but it means that a force is being applied to an object through a distance. So for instance, when I'm holding my book, am I applying a force? Yes, I am. Based on Newton's laws, right? If I were not, then the book would be falling to the ground. Gravity would be the force acting on it, pulling it to the ground. And you explored gravity yesterday in the Edpuzzle videos. Right? So I am applying a force to this book, but the book is not moving. So I am not doing any work. Work only occurs when the force is being applied over a distance. So when I lift this book to shoulder level, I have done work because I've applied a force and I've applied the force over a distance that's traveled by the book. When I lift it above my shoulder, I have done work because I've applied a force all the way the distance that the book has traveled. Okay, getting some exercise today. All right, so when force is being, I left out a word, applied to an object, sorry about that. Oh my goodness. I'm not going to start all over. Please pardon me. A force being applied to an object over a distance. So, work, we said that energy is the ability to do work, and work is when force is applied over a distance. So, the mathematical expression, the quantitative expression of this phenomenon is that work is equal to force times distance. Now, let me show you another distinction. Okay? The force has to be applied to the object in the same direction that the object is moving. So, force being applied to an object over a distance. Right? So, if I'm holding this book and I begin to walk towards you, is the book moving? Yep. Am I applying a force to the book? Yep. Did I do any work on the book? No, I did not. So let's think about why that would be the case. Yes, I'm applying a force to the book in this direction, right? I'm applying an upward force, which is why the book is not falling to the ground. When I move towards you, the distance that the book traveled was parallel to the floor. So the book traveled this way. The force that I applied was perpendicular to that. The force that I applied was this way. So I did not do any work on the book itself because the force has to be applied in the same direction as the distance or the movement of the book. So when I lift the book, I'm applying the force in the same direction that the book is moving. All right. So let's add that piece to our definition. A force being applied to an object over a distance in the same direction of the motion. So holding my pen, I'm doing no work on my pen. If I lift my pen, yep, I'm doing work. If I simply walk with my pen, I'm not doing any work because the pen is moving that way. The force being applied to the pen is up. Okay. All right, so we have a definition of work. We have an equation for work. The work is equal to force times distance. And the unit for work is the same as the unit for energy. So I told you a few minutes ago that energy was in units of joules. So work is also in units of joules. So my unit for work is, I don't know if you can see that, is a joule. I apologize. I'm trying to clean up my writing. All right, let's write that again. The unit equals a joule. How about that? Okay. So we've defined energy. Energy is the ability to do work. We've defined work, which is a force being applied to an object over a distance. And then we specified that that force has to be applied in the same direction of the motion of the object. So you have to have some movement for work to be done, and the force has to be in the same direction. So if I push my pen towards you, have I done work on my pen? Yes, I have. Because the force that I applied was in the same direction of the distance that was traveled by the pen. Okay. All right, so I'm going to switch our, I'm going to switch our visual just a moment so we can consider together. Some scenarios to determine whether or not work is done. Because we have to know by definition whether work is done in order to determine whether or not we actually have to employ the equation to solve for it. So I'm going to shift my camera down to a piece of paper and turn it around so hopefully you can see it. All right, so I'm going to look at, let's see if we can zoom in. Yeah, there we are. Okay. So this sheet will be posted today because we're going to use, I want you to have it for referral, but also because we're going to do some practice problems. And while I'm going to do a few examples with you, there's also an example here. All right, so we're going to look at the following situations, A through E, to determine whether or not work is done or not. So an ice skater glides for 2 meters across the ice. So is work being done? Nope. Work is not being done. Okay. So the ice skater, in fact, let's illustrate. So the ice skater is gliding across the ice. Draw us a little image, the ice skater. Okay. Gliding across the ice in this direction. So it travels some distance, but where's the force that's being applied that's causing the ice skater to move? Okay. So there's not an external force that's pushing the ice skater in this direction. The force is coming from his feet on the ice, which is actually in a different direction. Our next scenario is the ice skater's partner lifts her up a distance of 1 meter. Is work being done in that scenario? So force is being applied to the ice skater, and they're traveling a distance, in the same direction that the force is being applied. So this would be akin to lifting the book, right? The ice skater, he has a partner. I can't draw that well, so, but bear with me. He has a partner. It's like his partner is here. If he lifts his partner, then the force that this person applies has to be in this direction. And if the ice skater is lifted 1 meter, then the distance traveled is also in that direction. So, yes, work is done. The ice skater's partner carries her across the ice a distance of 3 meters. And so if they're carrying her, oh, that's terrible. Let's see. Let's make that, I don't even know how to make that better. They're carrying her, so I'm going from bad to worse. Sorry. They're carrying her 3 meters this way. What's the force that's being applied? The force, he is holding the ice skater, but the force that he's applying to hold her is in that direction. But he's traveling in this direction, so no work is done. After setting her down, the ice skater's partner pulls her across the ice at a distance of 10 meters. Again, now they're holding hands or something. He pulls her across the ice. The force that he's applying to her is in this direction, and the distance that's being traveled is also in this direction, which means, yes, work is being done. And then finally, after skating practice, the ice skater lifts her 20 Newton gym bag 0.5 meters. So she's lifting in this direction her gym bag. Boy, this is terrible, sorry. Lifting her gym bag in this direction. The force that she's applying to the bag is also in this direction. So is work done? Yes, it is. Okay. So we determined, based on the direction that the force was being applied and the direction that the object was or person was moving, whether or not work was done. Okay. Same direction as the force applied, work is done. If, and this was supposed to be a picture of them holding, in this one, the force that the skater is applying to her is up, is that direction, but the distance that's being traveled is in this direction, so no work is done here. So right now we should know at this point, we should be able to define energy as the ability to do work in units of joules. Oh, we should be able to define work as force being applied over a given distance. They both have a unit of joules. We should be able to determine, based on a scenario, whether work is done or not. And now we're going to spend a few minutes using the work formula, doing a few calculations, calculating how much work is done. So let's take a look at a few examples. I'm going to do a few with you and then ask you to do a few. Can't see that. That doesn't help you, does it? Okay. All right, so a woman lifts her 100 Newton child up 1 meter and carries her for a distance of 50 meters to the child's bedroom. All right, so we have to determine what's happening in the scenario, because what I know is that your tendency is to start pulling numbers. So your tendency would be to look at this. What value does 100 newtons represent? It represents force, because force is in units of newtons. So the woman lifts her 100 Newton child up 1 meter. So there's a distance of 1 meter. Then she carries her for a distance of 50 meters. So we've got to figure out in which of these scenarios is work being done. Sorry, let me pull out so you can see. There you go. All right, so when the woman lifts her child, we'll just make it a little baby that's swaddled, she's going to apply a force in this direction, and the movement of the child is going to be in this direction. So work is done. When she carries her for 50 meters, she's applying a force in this direction, but the distance traveled is in this direction. So there is no work done over that 50 meters, not done to the child, okay, or done on the child. So to find work, we've determined the force that was applied over the appropriate distance. So work is equal to force times distance, 100 newtons times 1 meter. Gives us 100. A Newton meter is the same thing as a joule. 100 joules, the unit for energy. Let's do another. How much work does a mother do if she lifts each of her twin babies upward 1 meter? So if we're looking at that, then the distance that's traveled, and since she's lifting them, she's applying a force, lifting, in the same direction that they traveled, up 1 meter. So distance is 1 meter, and the force for one baby is 90 newtons, but she has 2 babies. So ultimately, she's applying 180 newtons of force. So work is equal to force times distance. And we get 180 joules of work being done. Let's find one where we're looking for, let's look at this one, because I want us to have to solve for a different variable. So I'm going to jump down to number 11. You did 150 joules of work. So work was equal to 150 joules. Please notice how I'm listing the variables as they're given in the problem. And the reason for that is each of you should have a physical science reference table. If you do not, please email me so I can send you one. If you look inside your physical science reference table, you'll notice, actually it's on page 1, pardon me, the front page is full of equations. So right now we know we're studying work, so we know that this is the equation. But over time, you'll have to discern from that list which equations to use. And the way that I can do that is if I know the variables that are given and I know the variable that I'm looking for. So I have 150 joules of work that's done lifting a 120 Newton backpack. So newtons are force. Weight is a force. I had you explore weight versus mass last week, and weight is considered a force because it's due to the force of gravity on an object, okay, or the acceleration due to gravity on an object. So we have work, we have force, we don't have distance. So algebraically, to solve for distance, I'm going to show you 2 different ways to do this. One is you can simply divide by what you don't need. If I'm solving for distance, if I divide by force, then it gets rid of it on that side. And algebraically, what I do to one side of the equation, I must do to the other side. So distance equals work over force. The other way is I introduced you to the triangle, a little shortcut for dealing with algebra. So if my equation is work is equal to force times distance, the way the triangle is set up is that if there's something in the top of the triangle, you're going to divide by whatever is beneath. If 2 variables are beside each other, you're going to multiply. So those principles tell me how I'm going to put the equation in the triangle. What's happening to force and distance? They're being multiplied. That's how I know they go in the bottom two slots. Because if they're beside each other, we multiply. And then work is left, which means work goes up here. Now, what that tells me is, rather than doing all of this, if I simply use a triangle, if I'm solving for D, I can look at the triangle and it tells me that I'm going to put work over force. So in this case, I've got 150 joules that I'm dividing by 120 newtons. And I will get 1.25 meters, because we were looking for distance, and meters is the unit of distance. Okay. So I'm going to ask you to do several of these to practice on the Unit 1 and 2 tests. It was some of the math gave some of us some difficulty, so make sure you do enough practice to feel comfortable executing the problem. Please let me know if you have questions. The sheet is going to be posted along with the numbers on the sheet that you're going to execute. Right? Please email me if you have questions. That's the best way to reach me. And please don't put a note in the assignment itself. There's no telling when I'll actually see that note. All right. All right. I hope that everyone has a great day. Bye.